Hi, everyone. Welcome to the future. We've actually been here a while. I don't know how old all you are, but certainly it's basically since the year 2000, I've been looking at the date and going, isn't that date supposed to be the sci-fi date? Isn't that supposed to be the future? But I think at this point, we can say the future has well and truly arrived, and we're starting to get used to that fact. But this is harder than expected, because this isn't really the future we were expecting. We thought we were getting flying cars and moon bases, and that really by now we should be talking to people with like weird crinkly foreheads. But most of what we've actually got in this future is more of these. The future, it turns out, is mostly made of computers. And this is good and bad. Personally, I hate cars, so I think flying cars would be even more of a disaster. And so far, computers are less of a disaster than flying cars would have been. But the result is that we're building a new world on these computers. And that's good and bad. Computers are, and software in particular, are a lot more flexible than the old ways of building computers. Obviously, we wouldn't all be here without computers because this is a software conference, but also I think a lot of the information, this was all organized on the internet, a lot of the information that we needed to learn what we do was on the internet. And this future with computers in, it's actually pretty good. But it does have some problems, because I don't know if you've noticed this, but computers don't work very well. And you don't even really need to go to the length that Raymond did and introduce multi-threading all over the place. We can't even really make single-threaded programs work very well. I think if I wrote down every bug I encounter in the course of a typical day, I wouldn't have time to do anything else. And that's a reasonably common experience. Software is great, but software is also broken. And apparently got the same slide twice. And some of the reason for this is that a lot of our ideas about how to write good software come from projects like this, from the Space Shuttle, or from other safety critical industries, like aerospace, or medical devices, or in theory cars, but cars don't seem to have quite got the message that they're a safety critical industry, see previous comments. And the Space Shuttle do a very good job of writing correct code. Someone told me the other day that every time a software bug escaped into the wild on a Space Shuttle, they treated it as if it were equivalent to having lost a Space Shuttle. They also told me that they only lost 100 Space Shuttles in the course of the program, which until I read the first part of that sentence was very scary. But yeah, I think 100 bugs in the wild over the course of the entire run of the Space Shuttle so far is pretty good. But the problem is that we don't work on Space Shuttles. We have a very different environment than this, and this means that we can't necessarily take the lessons of the people who write software for the Space Shuttle and go, yes, we're going to write great code like these people, and the world is going to be a brilliant place built on rock solid software because we've all done our jobs correctly. Because there are a lot of differences with the Space Shuttle. One of the big ones is money. I have a long separate talk that I do about this, so I'm not going to go into this in much detail, but basically, I would love to have the budget the Space Shuttle program does. It's not as big as everyone thinks it is, but from my perspective, it still seems huge. The other is users. Most software has a lot of users compared to the Space Shuttle. There aren't that many shuttles, and they're running on an even more constrained environment than a Mac, so they've got a lot of say on how their software runs, and they've got a lot of control of the environment. And in particular, very few of their users are evil. Like, if if you're using the space shuttle software, then you're probably in the space shuttle, which means you probably don't want to break the software. Bad things happen to you when you do this. And most of our software is not like this. We do have to worry about not just use of the software, but we have to worry about misuse of the software. So although a bug in our software is probably not going to kill anyone, it might cost us a lot of money because someone's found a great exploit for buying books for -pounds, for example, and suddenly we're sending them money if we've implemented that feature. And along with these users come their computers. And these aren't just one computer. They are computers running different operating systems in different configurations in different countries. As most of you are probably painfully aware, not everyone has got the message that ASCII is not an acceptable encoding anymore. And you've got to deal with all the complexities of Unicode, all the complexities of different locales. A friend recently discovered that his game wouldn't play in Turkey because Turkey has interesting rules about case normalization in Unicode text. And their time zones are endless fun. And we've got to make our software work in all these different configurations. And it's not just each of these individual things, it's individual combinations of them. And it's just a huge range of diversity of environment that most safety critical software doesn't have to deal with. And by the way, we have to do all of this really quickly because the development process for safety critical stuff gets to spend time on this. We mostly don't. By and large, if you are taking 2 years to develop your software, then someone else has shipped before you and your software isn't wanted by the time you finished it. Oh yes, and also most of your software actually looks like this because we're all under the impression, I think, that the code we write is the software we ship. That's largely not true. One of the great things about modern software development is open source software. And the fact that we can build on this and we can use it to expand our capabilities far beyond what we can do ourselves. But the result is that almost all of the software that we're shipping is not actually under our control. It's of potentially unknown quality. If there's a problem with it, we can't necessarily immediately fix it because we don't want to maintain our own fork of the open source software. And we don't necessarily know what it was we're running. So another fun Space Shuttle fact for you. There is more Python code in the Python standard library than there is code in the Space Shuttle. So every single piece of software you write is already larger than the Space Shuttle. That's not counting the interpreter, that's not counting C extensions, that's just significant lines of Python code. There's, I think when I checked, about 450,000 significant lines of Python code in the standard library, and there's about 400,000 lines of code in the Space Shuttle. And by and large, this isn't a slight on open source software. It works far, far better than we could ever reasonably expect for something that someone gave us for free. But it is a thing we need to bear in mind. And I just pressed the wrong button. And the classic approach to keeping all these bugs under control is testing. And I consider fuzzing a sort of testing, so I don't think Raymond's example of why testing isn't enough is correct. I think it just means that you need more testing and different types of testing, as I'm going to be showing you. Because our existing models of testing, they don't really fit into this future that we're building. Because they were designed for the large projects, for space shuttle age, for things where we can be very obsessed with process because we can take the time to get it right. And in particular, one of the biggest problems with testing as we currently practice is that almost all testing you do is manual. I know you think you're doing automated testing, but what you're really doing is you're doing repeatable testing. You have done a manual test, and then you've taught the computer to parrot that manual test. So you don't have to type the test out twice, but you did have to type the test out once, and the computer will never discover a bug in your code that you didn't discover first. And fortunately, that's something that we can fix. Because we do have all these computers. And we can, as well as the computers being the problem, to some extent the computers can also be the solution, because we can set our computers doing true automated testing and going out and looking for bugs in our software for us. And there are quite a variety of ways of doing this. I'm focused on one because that's what the software that I work on does, and that's what I'll talk to you about today. And it comes originally from a Haskell library called QuickCheck, and you don't need to know any Haskell in order to understand anything I'm about to say. That's part of the hardest part of what I've been working on, is to make a lot of these ideas idiomatic and working well with the Python ecosystem, so that we as Python programmers can start to take advantage of these ideas and move into the 21st century of software testing. And hopefully that's readable back there. But the core idea of this sort of testing is more or less the same as the core idea of your normal sort of testing. This is using PyTest test syntax, but it will work just as well if you're used to unit test. I just like py.test better. And the idea is that your tests are almost normal, but you augment them with a source of data. This one's just a silly toy example to demonstrate the functionality. We've got our test booleans are not integers function, and we're augmenting it with one source of integers and one source of booleans, and we're asserting they're never equal to each other, which of course is false in Python, one of my less favorite Python features. But this demonstrates like the basic ideas of how these work. We write these tests, we use the hypothesis is given decorator, which says augment this test with a source of data. And we use what hypothesis calls strategies to then specify what sort of data we want. And these are two of hypothesis standard strategies. We won't see any very complicated ones in this talk, because it turns out that the standard ones are often sufficient to requirement. And then hypothesis runs this test by default about 200 times. It tries different things. And if any of them fail, it tries to produce a nice simple example to demonstrate the problem for us. And here that was 0 and false. Later we'll see that it can be a bit more complicated. And rather than walk you through more toy examples, I thought I would show you some of the examples that people have found in the wild and sort of some of the bugs in the Python ecosystem we've been discovering over the last year since this has sort of started to really hit production and start to really be used in the Python ecosystem. Here's the easiest way to use this sort of thing, which is that you don't really test anything, you just call some of your functions with random data and see if they ever crash. And that turns out to catch a large number of bugs in Python programs, because it turns out to be really hard to write Python functions which are even correct enough to not crash. Here's something from a function called a small library called binary or not. The idea is it's just a detection in code that you can pass a file to it, and it takes a guess whether this was meant to be a text file or not. This turns out to be a surprisingly hard problem. All the bugs I'm going to show you, by the way, except for one, I think, have been fixed already. In this particular case, what's happened is that binary or not has run afoul of the problem mentioned with open source software, which is that it's not under your control, so you're not as familiar with it. That's not fair. That's not a problem with open source software. That's a problem with libraries in general. And what's happened here is that it's discovered that the cardet library, which is designed to detect encodings on something, another problem that's much harder than expected, will often say, yes, this is definitely this encoding, and it turns out that you can't actually decode it as that encoding because it doesn't ever check decodability. So what's happened is that binary or not has taken a look at this, decoded it via the encoding that cardet swore blind that it was actually valid for this file, and it wasn't valid for this file. And so the function crashes. And that was relatively easy to fix once we knew it was there, but this is a program that, in principle, it's supposed to be safe to pass any file that someone has handed to you to this program, and it didn't manage to be correct. That's not the author's fault. It's very hard to write correct code. But this sort of testing discovered it in about the simplest possible way in about 2 minutes to write the test without any understanding and a couple of seconds to run it. Apparently it's pick on Mercurial today, because here's a bug in Mercurial. Similar scope, but slightly more interesting test. Mercurial represents a bunch of things internally using what's called UTF-8b. And UTF-8b is a way of taking arbitrary binary data and representing it as valid UTF-8 encoded Unicode text. That's about as much as I know about it. I tried to look at how this encoding was actually supposed to work, and I just went, but one of the nice things is that without knowing what it's supposed to do, one of the things you can do with encoders is you can check that there's a round trip. If you encode something and then you decode it again, you should get the same thing back, otherwise something's gone wrong. But we don't actually get to that, this just crashes again. Like I said, it's actually very hard to write Python code that is correct enough not to crash for interesting real-world problems. And I did know at one point what caused this, but basically, I think what happens is it strips one too many bytes from this when trying to turn it into UTF-8. And once they fixed this bug, they did then find another round stripping bug. And that didn't crash, but did give the wrong answer, which in many ways is worse. And UTF-8b isn't heavily used inside Mercurial, or they would probably have found this just because it broke for a user, but it's used enough, and Mercurial's been sort of in widespread production use for about 10 years. So you sort of hope that the bugs would have been shaken out of it by now, but turns out not really to be the case in a lot of places. There's actually a bunch more fun bugs we found in Mercurial with some recent work, but it involves a whole bunch of advanced features that takes an entire talk to explain, so I can't really get into that. But it turns out the Mercurial shelve extension, which is like git stash, it has a bunch of interesting edge cases that I don't think have currently been fixed. Here's a nice general simple problem in which Python really is broken. Sorry, Raymond. I think this one is fixed in 3.5.1 actually. But one of the nice things in Python 3, which you should all be using by the way, is it's got a statistics module. And here you can use the statistics to calculate the mean of a list of numbers. And here all we're doing is we're taking that mean and we're asserting it should be something vaguely reasonable. You shouldn't get a mean which is larger than the largest element or smaller than the smallest element, because the mean is supposed to be representative of the range of data. Unfortunately, the function crashes again. Crashing is actually better than every other implementation I tried of calculating the mean in Python, by the way, because everything else just gets the wrong answer. I've read about 30 pages on how to calculate the mean of a list of numbers, and at the end of it, I couldn't even keep the answer in my head long enough to escape the paper. It's a very hard problem, and the statistics module largely works around it by using arbitrary precision rationals as the intermediate, but then when it tries to convert back that ends up, the way they were doing that was wrong if the denominator was too large. The statistics module hasn't been too widely deployed in practice, so I'm not very surprised that it has bugs, particularly because all code that deals with floating point numbers has bugs, but it's always nice finding Python bugs. Here's another Python bug, by the way. Unicode. Also, all code dealing with Unicode is broken, and you should definitely be using Hypothesis to test your Unicode, because you probably, sadly, people usually don't care about floating point bugs because they just go, oh, those are silly numbers. But Unicode, it's a real problem. So this test is about Unicode normalization. It says that if a Unicode string is normalized already in this NFC form, which I'm not going to explain what it means because I only half understand what it means myself, then you add something to it which pads it with a bunch of dummy ASCII characters that should prevent it spilling over into the next string, and add another string to the end. Then it shouldn't change the normalization by adding that unrelated string. And that's not true. What turns out is that CPython has a fast track that checks if the string is normalized, and if the string is normalized already, then it doesn't do anything. Unfortunately, the isNormalized check isn't the same as the normalization code, and these don't agree with each other, and as a result, there are strings that would change if you normalized them, but Python thinks are already normalized. And so this happens when you basically add something to the end that forces the string to be denormalized. This one's a cheat, sorry. This is a real bug. This bug was discovered by Hypothesis, but in the current version of Hypothesis, this test can't detect it. The actual test that ended up doing this was an end user's test of their own code, which involved much more complicated transformations on Unicode that did eventually produce this problem. They seem to run into a lot of interesting Unicode bugs that way. I'm going to be fixing that in a later version of Hypothesis so that it can do more interesting things with denormalization. Here's one from another end user case where this is Hynix bindings to the Argon2 password hashing. So password hashing is when you don't want to store plain text passwords in your database, because we're all not storing plain text passwords in our database, right? So you want to create something that you can later verify that it's the right password without storing that it's the right password. And the way we test that is simply that we create the hash of the password, and then we verify the password we just had against that hash. That's what's supposed to happen, right? You should be able to verify that they're the same thing. And that works. By the way, Argon2 is a new password hasher that won a competition, so it should be relatively solid code. And the basic test does work fine. But then Argon2 has all these interesting config parameters. And it turns out that all sufficiently complicated config systems mean that your software is broken, because you've got this giant combinatorial explosion of parameter combinations, which, if you're doing manual testing, there is no chance at all that you have tested all the interesting combinations, although in this case it turned out to just be not all the interesting ranges. Basically, what we found out was that there were a whole bunch of ranges of parameter values that if your config was out of those ranges, then then the password would just fail to verify against itself. And this bug would probably never have escaped into production because it's a bit too obviously broken when it breaks, but it's sort of interesting because this was not a bug in the bindings. This was a bug in the underlying C library, and all bugs in C library should terrify you because basically C is unsafe, and thus potentially any bug in a C program is exploitable. I don't think this one is exploitable, but I'm never confident saying that. And we're doing actually very well for time, so hopefully you'll have lots of questions after this. I've been talking mostly about testing libraries and sort of these cute little examples because those are much easier to fit on a slide than anything else. But this is starting to see a lot of increasing use in the real world, and a lot of people are using it for testing these applications, and it's been going very well for them. And it supports most of the interesting things that you will want to be testing. There's custom Django support. If you use Django, you should definitely check out the custom Django support because it's great. It will automatically introspect your models and just go, oh, I know how to fill in all these fields. And then you've got custom fixtures for free. It works well with NumPy. It works well with all the different unit testing frameworks. And it's worth checking out. And in particular, I have a workshop tomorrow if you want to learn how to use this. We'll go through a bunch of examples that are not actually much more complicated than this, but you'll get to write the tests and figure out how it works, because based on what I've seen of Python code in the wild, and of code in the wild in other languages too, Python is not atypically bad at this. The code you're running in production is probably quite broken, and there's really no way to fix this without getting the computer on board and helping you test things out. And I've somehow finished my talk about 10 minutes earlier than I intended to, sorry. Because that's actually all I have to say now. Thank you very much.
Thanks. Вопросы?
Thanks for your talk. Can you describe any cases where quick check approach don't work?
Okay, so the question was where the quick check approach doesn't work. And mostly it should work in anything that's testable. There's no real sense in which there are things that you can test that you can't test with this. The two things that are often limitations is that one of the most popular ways of testing is that you run your test code and then you copy the answer into the test and see what happens and say, yes, that was correct. And generally, I'm not a fan of that sort of test, so I don't really mind that this doesn't work here, but it does force you to understand the properties of your behavior much more than you otherwise would. And the second case where this doesn't work is if your tests are really, really slow, then this will probably not help that much because it relies on running your tests lots of times, which is dependent on their speed.
Thanks.
Yeah.
Another one?
There was one back there.
Поднимите руку, если у кого-то еще был вопрос. Я бы забросил куда-нибудь.
How is the smoke data generated in those mock generators? Is it some simple like for I equal to this, or there are some edge cases being tested?
So the data is generated mostly at random. There's a bunch of sort of quite finely tuned distributions and a relatively complicated underlying fuzzing engine. And what it tries to do is generate random values that are likely to trigger bugs. So it knows about some special values, like the floating point one will specifically try to generate bad floating point numbers like infinity and not a number. And the list generator will deliberately try things like what happens if I put duplicate elements in this list. It's essentially a large number of quite finely hand-tuned distributions. And then once it has a failure, it also has shrinking rules, so it tries to reduce the data to simpler examples, because often what happens is that it triggers bugs with really complicated initial values, which you're never going to want to look at, and then sort of cuts them down to much simpler ones so that it can show them to you. Okay, more questions?
Okay.
Hello, thank you for the talk. And I have a question about performance of such testing. Let's say we have some methods which takes 4 or 5 arguments. Mm-hmm. And as I understand it, each of these arguments independently will be getting mm-hmm. random values, and we'll have to run Cartesian product of all the. Let's say if you have 3 arguments, all of which can mm-hmm. take x values, so we have to run x in the third power tests. Am I correct? Does it affect performance of the testing?
So that's not how the number of tests is chosen. It will always run a relatively fixed number of tests, regardless of the number of arguments you have, and it just randomly chooses them and doesn't try to do any sort of exhaustive enumeration. In terms of test performance in general, for most cases, the performance is basically, it runs your test n times and it will take n times your normal test runtime. For very complicated data where there's sort of large objects being generated with lots of dependencies amongst them, that's something that doesn't work very well right now and for complicated cases, it does tend to slow down a bit. But for certainly anything like what we saw in these slides, the performance is simply that it's running your test multiple times, so it will take proportionally longer.
Thank you.
More questions?
Все?
Okay.
Okay. Thank you, David.
Mm-hmm.